at the tricrystal point, because you basically have rings here, 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 and here. In this case, you don't have a number of pi junctions, so no activity, no half-flux quantum, only here. And if you cool the sample in a bit of magnetic field like here, you see that you have plenty of families of Josephson vortices or Abrikosov vortices, but here you still have the semi-flux, half of the other ones. Again, and I want to stress that this is spontaneous. No, you are not adding, so the energy comes from the pi junctions. And about that, this could be also engineering with the 20 group, and actually by using ramp-type junctions, they could somehow made these facets, and for each facet generate a pi loop. The only unfortunate story about this is that it was, it's not all ITC. This you need niobium counter-electron, so it works always at low temperatures. Just to give you, to stress how rich is the family of vortices here, I want to show this picture that we took with John on one of bipedactyl samples, again with green boundaries. And here, for instance, you can see that these are Abrikosov vortices, which are along green boundaries. These are these Josephson vortices, Abrikosov vortices. These are this is at 001 film, so vortices are in this direction. This is 103, so they are in the other direction. And all this magnetic activity is along the boundaries of green boundaries. And again, this is somehow very interesting, but still left something dead at the end, because the idea of generating these spontaneous currents in special corners for different objectives, but still you can do that, but not in a very reproducible way. That's the problem. Another wonderful type of junction is the one including ferromagnetic junctions, because you basically mix superconductivity and magnetism. So it's extremely interesting, because you mix two things which are apparently one against the other one. And obviously there's been one of the big themes of vortex project of Victor for so many years, and we have had so many years in our community discussions about these two communities. And again, I would like to stress also from the application point of view, we have the idea is that we may have spin polarized currents. And in terms of Josephson junctions, there are two very remarkable examples. This is a beautiful experiment by Ryazanov group, where by varying the thickness of the barrier, you can pass from a zero junction to a pi junction just by changing the thickness of the barrier. And from the very applicative point of view, there is a lot of interest for using them as a memories, these Josephson junctions. That seems to be one of the missing parts for digital electronics, to have good memories. And these kind of junctions are extremely promising if suitably mastered. And also something very interesting from the fundamental point of view is that for these junctions, it's expected that if properly built spin mixers, you may have triplets passing through the barrier. With all that it means in terms of possible advantages and fundamental physics. And there are different groups. One of these is, for instance, the Cambridge group. And here it's just to quickly highlight that, they use different junctions, and they use a lot of different materials. Also the Birch group, Northeastern, works with that. And so there are different materials, different spin filter efficiencies, but the key role is here about the barrier and the spin mixers. As superconductors, usually they use niobium or niobium nitride. Again, I would like another very remarkable story is that this work, I mentioned before as a memory, and the idea is that basically these junctions keeps memory of the history. So depending on the way you apply magnetic field, you may have different states, as reported in these IV curves. This is the work by Rezanov and Mukhanov groups. And what has been done together with them, that obviously would be discussed by Dr. Roberta and Davide, is that we are able somehow to influence and to change these two states by applying microwave. This is interesting because you don't need, in terms of some more complicated devices, you don't need a line to apply magnetic field. You can change the state of a junction just by applying an RF pulse. And so now we are back after this overview about all different junctions where there is a lot of materials issues combined with mesoscopic and nano issues, more to try to understand what we can learn more from a closer inspection of the responses of a junction, from IV curves and from studying the fluctuations of the junctions. I start from IV curves. This is an IV curve of weak link, typical rounded shape this way. You would measure the same with the low angle bicrystal YBCO junctions. If you change the angle, or in this case, if you start working with a barrier, you start seeing a rounding. But finally, when you increase the misorientation angle, or for a junction, when you have a barrier, you pass to this characteristic shape of RSJ model that yesterday was outlined by Dieter, and we will briefly mention now it's necessary for our aims. Again, here we are somehow decreasing JC. JC is the measure of the coupling between two electrodes, depending on the barrier or the weak link which is in between. If we have a barrier that we model as increasing capacitance, so we don't have anymore a metallic barrier, could be copper between lead, but we have aluminum insulator between niobium, IV changes dramatically like that. So this is the effect of the capacitance. We have a bistable state, and we have the supercurrent here. And if you are around here and you increase current, you switch to the normal state. Obviously, this is the perfect ideal niobium junctions that you get for low JC values. But these are relatives of this one, where you may have some kind of sub-gap currents around here. All this is fully understood and described by the RSJ model that we don't need to discuss further, because yesterday Dieter explained you where they come from, these terms, from the modeling junction with the conductance and the reactance here. What is interesting is that we have this washboard potential, and this washboard potential is somehow a translation of the phase, of the behavior of the phase of we'll see as a moment with electric measurements. So we'll have that when the ball, that is the capacitance proportional to the capacitance of the part of the junction, will roll down, will be in a resistive state. If we are in the superconducting state, we stay in one of the valleys. And so here, the slope of the washboard potential depends on the current, as we can see here. So this is for zero bias, so we have just simple sinusoidal function. When we increase the current, we get this bending, and then obviously we change the condition for which the ball could throw down the washboard potential. What is extremely important for what we're going to develop soon is the way these switching happens. This is a stochastic process, so it's not deterministic. And here enters really the behavior of the junction and can tell us a lot of things about fluctuations and macroscopic quantum tunneling effects. So we'll study exactly these fluctuations. And we will study how, the width of the junction, how will depend on temperature. Just for everybody, what is really extremely exciting is that you have here the phase. This is the macroscopic phase of the condensate. When you are for zero bias, you have here, and you have your experimental point is here. But if you measure IV curves, and you are moving around here, you are changing the slope, and at some point you will see resistance in your IV curve. So it's amazing how this, I would say stupid in some sense, measurement of IV curves is a direct picture of the macroscopic phase behavior of the junction. And this is crucial for what we said at the beginning. If we want to use this macroscopic wave function, we have to pass through the simple measurement to understand if this is possible. Because this will be, we will use them to understand what the macroscopic wave function is doing. And if the macroscopic wave function is doing typical things of an electron, like tunneling, like zero motion, like quantization of energy levels, so this means that it's valuable for doing a quantum device. So what is also should kept in mind is that these junctions, this RSJ junction model, really has been developed in so many different ways that basically all IV curves are described by of whatever device are described by changing the capacitance or whatever. To the point that has been also developed the tunnel junction model, where the resistance is replaced by another current phase relation. And here, this gives all possible artifacts that you can observe in real Josephson junction. So what I want to stress is basically, even if there are some kind of phenomenological models here, more microscopic, there are all the tools to describe IV curves. So in other words, if you have an IV curve that cannot be described by any of these models, you should worry, or there is some other new physics, or there is some artifacts. This is all very well understood, and again, on something that we'll soon get into, this is RSJ model. If you add an additional normal state resistance here, this is the TJ model. All models have some kind of very wide predictions on the dependence of the ratio between the critical current and the retrapping current. This is just to say that we have all tools and fingerprints to fully characterize the junctions. And if they don't fall in any of these things, you should be aware that something else may happen. What I want to say is that basically, if you want to do a qubit, probably you are just happy you have the two states. From my point of view, this may be very different. They may be these kind of jumps, they may have very different dissipation and may have different physics and mechanisms, and even intrinsic noises. And this is not only for the new generation of junctions, like you often observe this on hybrid junctions with ENAS nanowires, where you see this kind of excess current, a lot of strange things, subgap currents. But this is clear since, again, the 80s. This is work done at Cornell and then later at IBM by by Alan Clay Sasser. And here, it was doing high quality submicron niobium junctions. And when the JC is low, you have perfect Josephson junctions. So you have the critical current, probably these are the junctions that we would use for digital electronics. But when you would increase the critical current, because you want higher ICRM products, you get into problems, because you have huge subgap currents, and this behavior is not classified by any of the models I've shown you a couple minutes before. So the point is that, and we'll discover soon that something else is happening. But again, the point is when you try to reduce the barrier, because the idea, if you want to increase JC, you are making your barrier very thin. When you make your barrier very thin, you cannot avoid pinholes. You cannot avoid pinholes, so you cannot avoid artifacts. And what is tricky is that also these junctions, they have Fraunhofer pattern. But if you plot them as again, these are the exposure out to oxygen is somehow the barrier thickness. So you see that when the barrier is thick, everything is reasonable. When it starts to be exposure very short and the barrier much thicker, you lose control and you don't understand how, you lose correspondence between RSJ behavior and these curves. You cannot associate them, any capacitance, anything. You have some kind of problems from an electrodynamical point of view. And I would be very careful in putting these junctions in any circuit, because I don't know their electrodynamics. I may have artifacts when working spanning microwaves. And about the return current, this is a huge, it's a big problem, because here I've told you, and you will see probably after the break, how these are the fingerprints of quantum physics, and the first step towards qubits, and to understand this macroscopic wave function of Josephson is really valuable to do a quantum circuit. But the retrapping current has been big, an issue. Look here, Leggett, Fish, and Chen, they say the return of hysteretic junctions is quantum retrapping. Just to tell you that these IV curves are extremely rich, and when the junctions goes back, also here there is some important information to contain that we have to read and decodify. Probably, so that we start scratch new. Okay.
So we have 10 minutes for questions.